Recording. So the question we started off with last time was as follows. Basically, we get a file with a bunch of that basically is username and then the time logged in. And it's formatted like this. Like Alice had this amount of time, Bob had this amount of time, had a session with this amount, Bob had a session with this amount, Alice had a session with this amount. It's all, you know, it's not sorted. It's only like, if it's sorted by anything, it's sorted by what order the session started in, right? Or what order the sessions ended in. So, you know, Carl, Dan, Alice, whatever. You don't have to copy this stuff down. This is just kind of the example of the file, you know, ... to show that, let's see, Zimothy, that's a name, right? And Alice again, right? But the point being is that there's been plenty of names, plenty of logins. We don't necessarily know who is in there or not. So yeah, we have to do, so we need to review and this file, and what we want to do is find out what is the average login time for each user. Okay, so the average login time for each user, if we want to calculate that, that's best stored in a map, because where the key is the, and in fact on what they would give us, and this was an exam in C++, it was, they gave us essentially the equivalent of this: public static map, where string was the username and double was the, and we had a double for the, geez, words are hard today. We have a double for the value, which is going to be the average amount of time that that particular user. And let's go ahead and do calc average session. And then what we're going to do is that this is going to take in a couple, this has to take in an argument. What argument will I decide to use today? I'm going to use the string file name. That's right. We're going to go full-fledged, basically just reading the file and actually doing anything. So we're not even getting a list. We're actually going to have to read the file. Okay, so let me just bump that up over here. So we're going to need essentially 3 maps today. Okay. The first is going to be our average time, which is going to be our output, right? New hash map. Okay, that's going to be our output. So we'll return that. Right. Next, what we're going to do is that we're going to create a new map. So these are going to be the ones that we're going to use. Map integer, num logins. So in how many times did that user log in? We'll count them. New hash map. And then map string. And this will be another, this can be an integer as well. Total login time is equal to new hash map. Okay, so a couple things to explain here. So first off, right, the way you calculate an average is you take the amount of time, you know, the average session for a user is you take the amount of time that user has been logged in, and then you divide by the number of times he logged in, and you get your average. That's how you get your average. It's the sum of each occurrence divided by the number of occurrences. So we have to do this for each user. So we're going to do, we have maps because we don't know who the users are. Now there is a way to do this with one map, and that's as follows. One extra, you know, condense these 2 maps into one map, and that's if you were to do basically a string to list of integer, and then and that would be login times. Basically, you create a list for each user of all the times they logged in. And then to calculate the average, what you do is you sum that up and divide it by the length of the list. Right, that's a valuable way to do it, but I'm not going to do it that way because I've already written the other two. So let's go ahead. So what we next have to do is we have to read the file. So scanner. So scanner is equal to new scanners. And then instead of doing system.in, we'll do new file to read the file. So we'll go on file name. We will need to put a, so we will do that. Import file. And of course, this will say, hey, you need to try this. So I'm going to just go ahead and do a try catch block, try, and then catch file not found exception, because that's it. And I'll just be silly and system.err.println. And if you haven't seen that yet, that's system.out. That's how you get your red error messages. .println file not found, no dice, because why not? Okay. So system.err, and by the way, you can't like color coordinate, because your system.out and system.err will compete to see who can print out. So there's basically it's whoever can get scheduled first. So anyway, so we're gonna try and read it. If we can't, whatever. Okay, now that we've got it, what we're gonna do is do scanner. So now the file reading. So while scanner dot, and I always like to use has next line, because that deals with it just makes sense to me to always work with text in terms of line, and then each string I can parse individually. So has next line. So while it has next line, string line is equal to scanner dot next line. Awesome. Okay. Now what I need to do is that I know the format of this. I know the way that this file is going to be broken up. It's going to be broken up into two parts, right? So I'll go ahead and in fact call it parts, because it's not going to stay. I'm going to break it up into separate variables right immediately after that. But all I have to do is line.split. That takes in a regular expression, but we don't need you don't really need one. You just simply say split to split on the space. Of course, if I leave that blank, let's see what happens. Nothing. Okay. So line.split, we're going to split on the space. And so that means I'm left with an array of size 2, because as far as what we're guaranteed our file is going to look like this. That's a guarantee. File is going to have string space number. So what I'm going to do is I'm going to basically say, hey, string user is equal to parts 0. And then string, sorry, not string, but int time is equal to parts 1, except that that's a string and I can't convert it. So I have to do integer dot parse int to convert that to an integer. Python had the right idea by having it, by basically being able to throw stuff into an int function, built-in int function that would just convert it. That was the right idea. All right. So next thing we need to do is, now that we've got this, is that we've got to populate our maps. So what we're going to do is, so first off, we basically have to, so first off, we only have to check if it exists in one map, because if it exists in one map, it's going to exist in the other map. So if num logins dot contains key user And yes, you could use get default or 0, but I'm going to do it this way. If we have it, so if we have seen this key before, what are we going to do? We are going to say, hey, let's go with int num sessions, or sorry, num logins. No, int logins is equal to num logins dot get user int total time is equal to, so I'm going to do both of them in this single if statement. Total time login dot get user, and then num logins dot put user logins plus 1, because that's the number of times they've logged in, and then total login time dot put user total time plus the amount of time that he's been logged in for. Okay, make sense there? And now, if it didn't exist, we just basically, I'll copy this, and it becomes, instead of logins, it's just, well, we've seen him once, and he's been in for this amount of time. Okay, so that's a lot of code for just populating the list. Okay, now that we're done populating, it's just for populating those maps. Now that we're done populating the maps, let's actually compute the average. So for string user in numlogins dot key set, so we'll get all the users. So for each of the users, what are we going to do? We're going to get in, I'll grab these two from up here and reuse them. The number of logins, get the number of logins, get the total time he's been logged in for. Okay. And now, I'm going to deliberately cause an error here. Also, it wouldn't be mathematically really correct to do it the way I'm doing it, but I want to cause this error, which is that I will do, so what is our final, it's called average time. Average time for that user is dot put user, and then total time divided by logins. So this will cause an error. Specifically, what's going to cause is required type double, provided type int. So this again is just kind of a minor thing that happens that's fixable as soon as you know what it's one of those quirks of Java, which is that right, if I did a primitive double, D is equal to the total logins divided by time, right? That works just fine, right? It automatically will convert a primitive int to a primitive double. And same here, if I did a double, capital D is equal to that, though you'll see that it doesn't convert a primitive int to a class double. Although, and this is what the confusing part is, if it would totally convert the primitive double to the class double using the process of autoboxing. Make sense? Yeah, all right. It's just one of those things with primitive, just basically primitives will automatically convert, classes will automatically convert to primitives of their own type, which is important because when we deal with generics, you're dealing with the class type. So, and besides, an average, you'd probably want a double anyway, and this results in an integer, right? We'd be cutting off some precious decimal points. So way, of course, to do that is just simply multiply by 1.0. And now that converts the entire thing into a double, which then gets converted into the double no problem. All right, and that's it. That last part is fairly easy, and now we've computed the average time for every user. I find this one good because it is really a good kind of trial of just like how to use maps. And if I were putting this on the exam, it'd probably like be worth a high amount of points because of how much you'd have to write. Or depending on the exam, I probably would provide all these parts. I'd probably provide the, like this entire part, because the file reading, asking you to do file reading on the exam is a lot. For Java, not so much in Python. Python's super simple because, you can do that outside of an IDE, but for Python, there's always the issue that you accidentally drag it into the SRC folder in your IDE versus your here, and then you waste 10 minutes trying to figure out path issues, and just it becomes a nightmare. Okay, so none of that. So don't expect to do file reading because file reading has its own issues. So let's go ahead and now work on some of the graph problems, which again are guaranteed to be on the final exam. So again, what I'm going to do is I'm going to look. We had the Harvard data structures final exam. And we had two different documents, and yes, this is the other one, which here they tested. So this one, which we didn't look at, tests a bit of recursion, if else statements for no reason. Then we've got some recursion, which is good always to practice. So this is, this is fun. This is like stuff that we did from 1068. So part of this is that there are multiple ways of doing this. Basically, you got to do your intro to programming, your object-oriented programming, your data structures, and your algorithms. That's how we do it in here, but some other schools, they do basically intro and object all together, or intro plus object, and then objects plus data structures, and then algorithms. So it's whether how you do it as a 2 or 3, as a 3 class sequence or a 4 class sequence. It all depends. So you'll see some bleed in some exams, like in some of the practice exams, though you get data structures and algorithms. And yes, our algorithm class is called data structures and algorithms. Even though we focus a lot more on the algorithms that use the data structures. So anyway, right, so we've got similar stuff over here. Some of the codes some of these that we've already done, but I wanted to go to the graphs. Ooh, wait. This one looks like an interesting one, and I have not seen this before, so we'll see. So let's see. The following array is to be sorted in ascending order. Which algorithm would cause the array to be ordered like this in the immediate? So this is a great question. Following array is to be sorted in ascending order. Which array is to be sorted? It will be ordered in an intermediate stage of the sorting process. Bubble sort, heap sort, insertion sort, quick sort with an initial pivot of 33. How would that even work? Well, whatever. It's not going to be that because it's not swapping correctly. And selection sort. Okay, so bubble sort. Bubble sort basically means that we're going to take the biggest item. It's always going to kind of bubble to the top, but 52 has gone all the way to the front, so that's just not going to work. So it can't be bubble sort. Similarly with selection sort, we can rule it out for the same thing. Selection sort is the one that has O of n exchanges, but always O of n squared comparison. So selection sort is the greatest one if you're actually going to be physically moving, sorting by moving things, like very heavy things. So its application is more to the physical world. Okay, so 52. So we want to go ahead but what you would do is you'd always take the smallest, either the biggest item and move it to the back, and then the second biggest item, move it to the second location, or more classically, the way you do it is you take the smallest item and move it to the front, and neither of which is happening here for selection sort. Quick sort, so what you do with the pivot is you take the pivot, and you do your partition function, but this doesn't look like anywhere in the middle of a partition function or after it. After the partition function, all the things that are left should be to the left of the pivot, and all the things here should be to the right. And otherwise, if you're doing it, then you want the pivot in the front, but everything is kind of mixed match with things bigger and lesser than pivots all over the place. So it doesn't look like an initial this. Now, similarly for insertion sort, what you're going to be doing is you're going to be sorting. Insertion sort's great. Basically, what we would be doing is 25, 25, and 47. Basically, we'd keep adding an item, we'd keep inserting the item so that it would, so the sorted portion keeps growing bigger. So you'd have a sorted portion of the array and an unsorted portion. So the third step would be 14, 25, 47. So for the insertion sort, what the key marker is that that section should always be sorted, and that's not sorted. Process of elimination says it's heap sort, and that makes sense, I think. Because when you're doing heapify, oh yeah, that totally makes sense. Yeah, so for heap sort, what you get is you get a max heap. But wait a second, this isn't a max heap, right? Because that biggest item is in the back. Right. Well, what you do is that basically when you heap sort, is that when you create a max heap and then you remove your frontmost item, okay, and then you move it to the back. So here's what I mean. Like this is in the intermediate stage. So they've turned it into a heap. So we've got 52, 47, 25, 33, 15. And 14. So we can see here that right now we've got a max heap. But once we have 74, it's like that's not a max heap anymore. And that's okay because this thing's actually been sorted. Because the way the sorting process works is for this is that to sort the next item, what we do is we remove 52 and we move it over and we swap it with 14 and then pretend it doesn't exist anymore. So 14 is over here and now we reheapify. 14 is smaller. So it's less important. So the bigger, more important number needs to move up. So 47 and 14 will swap. And then 47 and 33 will swap. And then the next thing we do is we take 47 and move it down there and pretend it doesn't exist anymore. So you keep doing that. It takes log n for each step, n log n, and you get a sorted array when you're done with it. So that's the way heap sort works. And of course, if you didn't know that, process of elimination would help you there. Okay. Okay, so we've got heap, remove, what is the big O time complexity? Well, here we go. So we didn't do that. Topological sorting isn't on the exam, but it's good to know, given this graph here, which of the following is not a topological ordering of the vertices. This might help you with your homework the last homework that you might be working on, or you might be dropping it, which is totally okay. So, so topological ordering means basically what we do is basically prerequisites. Basically, we don't want to travel to any node before we've been to the node before it. So the way you do that is via Kahn's algorithm. You remove, so for instance, for this one, we can remove A, which removes these edges. And now what we continually do is that we look for and remove a node without any incoming edges. B has no incoming edges, so that's fine to remove. C has no incoming edges. D has no incoming edges. E has no incoming edges. F has no incoming edges. Neither does G nor does H, so that's fine. Similarly, this last one, D has no incoming edges, we can remove that. E has no incoming edges, we can remove that. A has no incoming edges, so we can remove that. Okay, okay, there we go. So A has no incoming edges, C has no incoming edges, nor does B. Then F has no incoming edges, then G, then H. So that's a topological ordering, and it's looking for the one that's not. So A, B, D. So let's go ahead and go look for the next one. A, B. So this is D I'm looking at. A, B, D, E, C. Sorry, A, B, D. I started reading the wrong one. A, B, D, E, G, F, H, C. Okay, that seems fine. And now C. C says A, C, D, B, E, G, F, H. And so B probably is our answer, where we get A, C, B, And then we try to remove F, but we can't remove F because we haven't been to D or E yet. So that's not a topological sort. All right. All right, so, oh, this will be good for reviewing our sorting as well. I'm not doing it. Okay, 2 through 3 graph. That's the same graphs that I don't like using for that one. Okay, so I'm going to pull up the other exam. So GitHub. So GitHub, Baby Rosen, destruct, firm, study guide.pdf. Download so that the links will actually be clickable. Some of them are, okay, here we go. So I'm going to go ahead and skip down to the graph section over here. All right, so here's an adjacency list representation of a directed graph where there are no weights assigned to the edges. Okay, that's a graph. Draw a picture of the graph. It's not a bad question at all. Okay. You know, I can't remember if I have a question that tells you to draw the picture of the graph. I think what I do have is that I give it to you as an adjacency matrix or an adjacency list, and then tell you to do ref, and then I will tell you to basically perform an algorithm on it, ref for search or depth for search. So draw a directed graph that is a representation of this. So we have A, B, C, and D. So A goes to B, C, and it also goes to D. Circle our nodes. B goes to A. So here's the node, and these are the edges, the connections they have. C goes to B, and C goes to D as well. So that's our graph. Another way to represent this is an adjacency matrix. Draw the adjacency matrix for the graph. That's even easier. Okay, that's even easier to create the and I'm going to just enter it in the same space. To create the adjacency matrix, right? We basically create a grid: A, B, C, D, A, B, C, D. Okay, so, and we put ones wherever we have a connection. So A has a connection to B, C, D, B has a connection to A, C has a connection to B and D, and D has no connections anywhere. That's it. All right, now let's look at a weighted graph. Considering the following directed graph. Not only that, it's a directed acyclic graph, right? Meaning that it has just directed edges and they don't have any cycles. So use Dijkstra's algorithm to determine the shortest path from 1 to each of the following vertices. Okay, first off, let's go ahead and rename that because that's terrible. What I'm going to do is that I'm going to take this graph, first off, full screen, so that I can make it a bit bigger. What I'm going to do is that I'm going to relabel these, okay? What do I mean that I'm going to relabel them? I'm going to basically create, so let's go ahead and actually, yeah. So we want to do Dijkstra's, and then we want to create a table basically where we have the distance from the initial vertex, and we want to go into our and basically we want to list what the predecessor is. You know, how do we, so in other words, we want to create the table that's the output of this graph. How much it costs to get to where we want to go, and then how we got there. Now, what I mean by rewriting this is that using numbers is terrible because we have numbers as edges, and I feel that gets confusing. So what I'm going to do is I'm going to copy this. And let's see if this works. Open up the whiteboard. Back to mouse. The whiteboard. And then drop this on here. Okay. And let's go ahead. Yeah. Let's go ahead and now relabel these as A, B, C, C, D, E, and F. I know that's kind of terrible looking, but I figured that's be a bit more. Okay, yeah, that's close enough. All right, so now that we've got that, let's go ahead and create our table. So we're going to be starting from A, and we want to calculate the shortest distance. What Dijkstra's is going to give us is the shortest path from A to any other node. So A. So let's go ahead and move a bit over here, and what we get is A, and then we're going to get the distance. Sorry. Node. Just previous node. That's all we need. Okay. Assuming my whiteboard cooperates. A, B, C, D, E, and F. All right. So first off, the distance from A to anything else to A to itself is 0. No previous node. Just gets there, right? For everybody else, we initialize the distance to get from A to anywhere else. Well, you can get to any node from A, but initially it's going to cost you infinite amount, if that makes sense. Right? That makes sense to everybody? Because that's what we initially know. All right. And now we use A to initialize the actual cost. So we can get from A to B with a cost of 2 and A to D with a cost of 3. Everybody following so far? Okay. I've done this a couple times in the videos, so, but I figure it's useful to see this problem here. So A to B costs. Okay, so now what we go through is that we are done initializing, so we're done with A. So let's go through, and we've got to basically figure out what node we're going to use to get more information next. So we're going to look for the node with the smallest distance. That's B. So we figure, and since that's the node with the smallest distance, we figured out what the smallest distance to B is. So we're done with that. We can now use B as the point to adding new information. So from B, we can get to E and C. So to get to E, we can get to E from B. And the total cost is going to be not 3, but 5, right? The distance is the total cost. We can get to E for a total cost of 5, because that's 3 plus the current cost to get there from B. Similarly for C, we can get there with a total cost of 7. All right, so now we're done with B. So now 2, 7, 3, 5. D is our next one. Okay, so let's go ahead and look at D. From D, we can get to C. We can get to C with a cost of 4 from D, right? 3 plus 1. 4 is less than 7. So we replace what we had. So the cheapest route to get to C is to go from D. And we can get there in a cost of 4. So now we're done with the edges. So now what we can do is that we go through. C is the smallest cost. So now we'll look at that. So C can get to F. C, it costs us 4 to get to C, right? Not 7 anymore, 4 to get to C. So the total cost to get to F would be 4 plus 2, which my son, who's 5, assures me will be 6. So no, the math isn't going to be too hard. Okay, and C over there. Then the next node to check off will be, we only have 2 left, so E is 5. 5 plus 4 is 9. That's not cheaper than the cost of 6 to get to F, so we don't update it. And then F has nothing else to to lead us to. We don't have any more nodes to visit and no more nodes we can reach, so we're done. Okay, so, and list the nodes in which they were processed. Well, they were processed in this order. We went here first, 1, 2, and then we did 3. Sorry, we did 1, 2, 3. And then we went to 4, 5, and then 6. That was the order in which we visited them. All right. So if V is the number of edges, V is the number of vertices, E is the number of edges, was the runtime of Dijkstra's algorithm in O of N notation. I believe it's E squared because we check every edge twice, which is, or rather it's V times E rather. So Wikipedia says, so here's the thing about Dijkstra's algorithm. The answer is it depends, as you'll learn in algorithms. And what it depends on is the process, right? When we did Dijkstra's algorithm, we had this entire process of basically, let's look for what the node with the smallest distance is, right? So the way Dijkstra did that in his initial paper was, I did it with V squared, which, so number of vertices. We look at every vertice and compare that to every other vertice, right? Basically, we look at this vertice and see, can we get to every other vertice from it? So that's the naive approach to it. You can also use a minimum priority queue, basically look through and basically say, hey, and that works out to B plus E log V. But then we can get even faster with Fibonacci heaps, which are these weird heaps, and they give you E plus V log V. So notice that this is no longer, that over here, we no longer have the edge as a multiplicative factor against the log V. So it really depends in terms of what you use. So I'm not necessarily going to go ahead and I'll talk about that, but in general, if we were just using matrix, you can always answer these as worst case scenarios O of N V squared, because it's never going to get worse than comparing every other node to every other node. All right, so let's go ahead and look at some of these others. So let's go ahead and look at some of the other ones on here. So, all right. So this is about priority queues. It's fine, we know about those. So, okay. So different data structures, we've seen lists, either a linked list or an array list, 2D or higher array, a stack, a queue, a hash table, a tree, binary search tree, undirected graphs, directed graphs, and directed acyclic graphs, which are directed graphs with no cycles. Why are those important? topological sort. Anything basically anything that's kind of a requirement chart, you got to do these things before you do these things. That's a directed acyclic graph. So for most of the for each of the following applications, indicate which of these data structures would be most suitable and give a brief justification of your code. I will be doing something like this on the final exam, guaranteed, just like you had on the second exam, because it's a good question or a good series of questions. Okay, map of the Puget Sound highway system used to display traffic travel times on a web page. The map displays principal cities, intersections, and major landmarks, the roads that connect them, and the travel times between these roads. Travel times along the same road may be different in different directions. So what data structure is that? Sorry? A graph, yeah. So what are the nodes in this? The vertices in this graph? Yep, the cities, intersections, major landmarks. And the edges? And what are the weights? Yep, travel time. This is essentially the classic model for a graph that you see in a lot of textbooks because you want a lot of times graphs are concerned about where you were going and how you were getting there, as opposed to nowadays what I like to do with these human relationships, essentially. Chessboard, we did this one. 8x8 chessboard used for a game of chess. Each square on the board is empty or contains the chess piece. So what data structure did we use? Yep, a 2D array. Computer model showing the dependencies between the steps needed to assemble a B787 airplane at Boeing's Everett plant. This really is Washington themed. Okay. So what kind of data structure is this? The dependencies between steps. Well, it's tree is close because, but here's the thing, right? Right, you want to do this before you can do this thing or this thing, but you can have multiple dependencies, right? You might have to do 3 different things before you do this, and this thing might actually have to be done before that too. So this is more of a graph, but what kind of graph especially? What kind of directed acyclic graph? Because dependencies cannot have cycles, because otherwise you get into a Kafka-esque kind of like, okay, I have to do A before I can do B, and I have to do B before I do C, but C is required in order to do A. That's not gonna, you can see how nothing would ever get done, right? So you can't have a cycle with dependencies. So this is a directed acyclic graph. A list of legal words in a Scrabble game. Come on, you can't use a data structure term. Yeah, but how else are you going to use it? A collection of legal words in the Scrabble game. We want to quickly check whether the word, but here's the thing, it's not necessarily a list. We want to be able to quickly check whether words used by the players do in fact exist in the list. So if we're using C, so if we're using a data structure for speed, what should we use? Hash map. Hash map, or more specifically, I would use a hash set, but hash map is just simply a set. A map is just simply a set with extra steps. Or sorry, a set is just simplified map rather. So describe the description of the inheritance relations between classes and interfaces in a Java program. It was tricky. You could argue tree, but you could also actually you can inherit multiple parents is the thing. So I guess not, right? You can inherit, you can implement multiple interfaces. So I could, like, it's hierarchical, but everything is from the root object. But you can have more than one parent class. So I would argue that this is another directed acyclic graph, right? You're not going to have a circular import though thing. All right, a history list recording sites visited by the user of a web browser. The new sites are visited as they added to list. The list also supports the operation of going back to the web page that was previously visited before going to the current web page and going forward to the next page visit. In other words, it's asking me the data structure to implement these arrows right over here, right? The back and forth arrows. What do you think? There's a couple different answers here. Yep, linked list would be able to implement both of them, or you could use a stack for one stack for the back arrow, one stack for the right arrow. All right, so this one, hey, we have a binary search tree node. All right, complete the definition of breadth, and now do a breadth first search. Write an algorithm that performs a breadth first search that prints the node values in the order they reach during the search. So you could use instances of other data structures, lists, stacks, queues, trees, graphs, whatever, and their operations if useful without having to give details, right? So we can use data structures to complete this data structures question, in other words. So in other words, a breadth first search of a tree, okay? Trees are just graphs, so we just can use the same kind of strategy we use for a graph. So I'm gonna open this up. I'm gonna grab my node class, new Java. Yeah, I'm just gonna work in here because I've already had this. So again, first thing you'll need to do if you haven't already written it is write this class, a node class, right? Don't need the comparables like we did last time, right? But basically you need an item, a left and a right, and a constructor ideally, but we don't really need that. More important is just doing this, public static. And then what does it want as our output? Oh, it wants to print it out. So public static void. Yeah, I'll do it as a static method. Public static e void breadth first search string, and then node e root. Now here's the thing, it's a tree, so you might think of doing recursion, but breadth first, but you want to do recursion if it's depth first. If it's breadth first search, you're not going to have such an easy time of it, because breadth first, what we need to do is as follows. We want to go through nodes in this order. If I'm drawing it, I'm going to draw the tree. 1, 2, 3, 4, 5, 6, 7, right? So we'd want to go 1 to then to 2, then to 3, then to 4, then to 5, then 6, and 7. And then I guess like if we didn't have anything here, we'd want to go to 8, you know? Make sense? So we need to go across, which is not the same. So to go across though, what we're going to use is the queue. Right, breadth first search means queues, depth first search means stack. So what we're going to do is that, and here's the nice thing. Normally when we do breadth first search, we have to care about whether we've seen it before or not. But since everything is only accessible from its parents, we don't even have to worry about that. All we need is the queue. Q is equal to, and that's an interface. So I think you have to do new linked list. Yeah. Sorry, just QEQ, just amused. I'm very easily amused today, apparently. All right. So, and then we're going to do, because it's not recursive, what we're going to do is we're going to say node E current. Actually, we're not even going to make that. We're just going to do Q dot offer the root as our initial starting point. Oh, it's not, sorry. Queue of nodes, my bad. Queue of nodes, offer the root, wow, the queue. Dot empty. Dot is empty, is not empty. So while the queue still has things in it, we still need process things in it. So what we're going to do is that we are going to basically say node, we're going to get the current node, E, I'm sorry, current node, current is equal to Q dot pull this is the DQ operation. Right, we get the queue, the thing at the front of the queue. And now what we do is that basically, let's see, it's all about printing it out. So I'll just simply do print out current dot item, print out the item in there. And then we need to go and actually enqueue the next nodes. So we're going to enqueue my left child, and then I'm going to enqueue my right child. Okay. And I have to handle the null somewhere, so I'll handle it now. Actually, what I'll do is I'll handle it over here, which is if current is equal to null, then I'm just going to continue. I'm going to just not do anything. Or I could just, yeah, you could do it a bunch of ways. I'm already doing it like this. I'm going to just keep going. So, right. So now I don't have to worry about adding nulls. I'll go ahead and add nulls to this queue all day and not have to worry about it now. So, so now what I do is basically, so I print out the item because I know it's not null. And now also, since I know it's not null, I can go ahead and do queue dot offer current dot left, current dot, and queue dot offer current dot right. And so now if I have a binary search tree, basically what I'm going to do with that is if I have this node, what I'll do is this will get added first, and then I'm just going to say add this child, then add this child, then so this will be the next child in the queue, and it will say add this child to the queue, and then this child to the queue. This will be the next thing in the queue, so it's going to process next, and it's going to say add null to the queue, and do this. And this child's going to be next, and it's going to say add my nulls to the queue. This child would be next and says add my nulls to the queue. This guy's going to be next. This null would be next, and it says I'm a null, skip me. And then this guy would be next, add his nulls, and then skip the nulls, skip the nulls, skip the nulls. So fairly straightforward, even though it's not recursive. All right. All right. So let's go back to the Harvard one because I saw some very interesting, more sorting problems over there, which I like. So, all right, the arrays below is to be sorted in ascending order. All right, in the initial partition step of the version of quicksort discussed in the lecture, with 36 being the pivot, how would the array be ordered? Okay, so we didn't do it like that. We always selected the first of their pivot, but they selected that one specifically. So here's what I'm going to do. If they want to use 36 as the pivot, I'm going to go ahead and put it over here because that makes more sense to do it in place for a. So what I'll do is I'll do 36 over here. So I'll go ahead and rewrite it over here. 36, 53, 71, sorry, 71, 62, 17, 46, 41, 23, and 12. Now the way the partition works is that we have an up. So we have right, we have basically we have the start and we have the end, we have the front, we have our start point and we have our end point. We also have our up, our down. And what we're going to do is we're going to iterate all the way up. What we're going to do is we're going to iterate looking up for the first thing bigger than our pivot. Okay, so we move up from going from the left to, so from the left to the right, we look from the left to the right, we go up the indexes looking for the bigger item, for an item bigger than pivot. Then we go down the indexes looking for a smaller item, smaller than the pivot. We found one, So we swap them. So 12 and 53. 12, 53. Then we continue. Up for the first thing bigger than the pivot. Down for the first thing smaller than the pivot. Making it nice and easy for us. So I'm not going to bother. So up 71, down 23, swap them. Up for the first thing bigger, down for the first thing smaller. Now we swap them, 17 and 62. Up for the first thing bigger. Down for the first thing smaller. These two things have swapped plate up and down, have crossed each other, so we are done. And if you see, we've got our pivot, everything less than the pivot, everything greater than the pivot. So now what we do, we need to put 36 into the middle so we can separate that into less, middle, greater. And we do that by swapping the last that we swap down with the pivot. So 36. 17 and 36. So after the initial partition step, this is what we do. The initial partition, and this is the initial partition because then we'd have to run quick sort on this and quick sort on this. All right, so I never actually went over radix sort this semester. Geez, you missed out. So let's go over it now. Radix sort is very interesting because it does not involve any comparisons whatsoever. Radix sort's runtime is also unusual. It is O of n, sorry, Wn. That W is a big asterisk though, because W is the word size, meaning how many digits are in it, or in the case of strings, how many letters are in it. Okay, so for ints, those are binary digits. So this is typically like 32 if you're dealing with ints. Now, keep in mind that 32 is normally a lot bigger than log n. Log n, in order to get to log n, in order for this to be better than log n, you have to be sorting billions of things. And it also takes up quite a bit of memory, but you're not doing any of your standard comparisons. Instead, what we're doing is that we would we sort things by looking at the least significant digit. So what we do here is that we'd have a queue set up for 0, 1 for each of the possible values of the digits, right? There's 10 possible values. So we have a queue for each of them. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so now we look at the ones place. We go through left to right and put them all into ones and look at the ones place. So 17, that ends with, that's the ones place is 7, that goes to the 17 queue. 53, that goes into the 3 queue. 71 goes into the 1 queue. 62 goes into the 2 queue. 36 goes into the 6 queue. 46 goes into the 46, it goes into the 6 queue. 41 goes into the 1's queue. 23 goes into the 2's queue. And then 12 goes into the 2's queue. 23 goes into 1's queue, 3's queue, and then 12 goes into 2's queue. And now what we go through in order of the in order of these queues, and we dequeue them. So 71, 41, 62, 12, 23, sorry, 53, 23, 36, 46, and 17. And notice that everything is now sorted according to the least significant digit. So that's our initial step. What do we do for the next step though? How does this actually work? Well, you keep going for as many digits there are. So next we would do the 10th place. And if you follow that through 71, 41, you quickly see that. So 6 goes into 62, 12 goes into here. You'll quickly see that everything gets sorted. And if we DQ everything, it will be DQ'd in order. If you had a 3-digit number, by the way, we would just prepend all the other ones with zeros. So this is how radix sort works. It's great because you actually have machines that do radix sort. No, thank you on the bubble sort, selection sort. We can skip that. And so anyway, just thought those were interesting. Let's say you need to sort an algorithm. Sorry, let's say you need to sort a collection of data that's stored in a singly linked list. Is selection sort a good sort algorithm to adapt for this problem? Why or why not? So insertion sort is great for a singly linked list because that's the way you're going to be doing stuff. You have to move through a singly linked list. You have to go through and physically insert something. So that's the best way to do it. If you're going to insert something, if you want to sort a collection of data stored in a singly linked list, merge sort probably your best bet because you can just move the nodes around from one linked list to a bunch of other smaller linked lists. Okay. Shell sort is definitely not, because the way shell sort works is that it's like insertion sort, but on gaps. So basically what you'll do is that like you have this, would have this, list of stuff. Okay. List of nodes. And then basically you do insertion sort on this one, and then one over here, and then this one over here. And then you'd move that section over and then do it on this one, and this one, which you'd have to seek for them. And that would just be, and then you'd have to go back and forth. And that would just be a pain for this. It works great in arrays and array-based stuff, but for linked lists, this is a terrible idea. So much time wasted, in other words, going through these. All right, so let's see if there's other interesting ones in here before we go on. Recursive backtracking. The knapsack problem. If you want to check something out, if you want to check this out, this is a worthwhile one, just like for really reaching, because this is something you'll cover in algorithms. The knapsack problem is a great problem. I'm not going to solve it here, but it's really, because I want to move on to something more practical for the exam, but it's worth thinking about. This is, the idea here is that you're a burglar, and you're burgling. You get to a place, then you get into your vault, and you've got a backpack. Now your backpack can only hold so much weight, but you've got a bunch of items. Now that painting's probably worth a lot, but that's going to take up almost all the space in your backpack. On the other hand, those gems are worth plenty amount, but they're not going to take up a lot of space. So you're burgling, and you want to maximize your burgling, right? So in other words, you want to fill up that backpack up with not as much stuff as possible, but with as much value as possible. That is the knapsack problem. So that, and that is like one of the NP complete problems. It's quite good. It's quite a good problem. But it's worth taking a look at. Because you can see that like anytime you're trying to maximize under some kind of constraint, that's the knapsack problem. Okay. So suppose you want to print a binary tree like this one, shown in reverse level order, so that the nodes of the tree in the diagram would appear in reverse alphabetical. You can use a stack, a queue, or both as auxiliary data structures. Describe the algorithm that would accomplish the task. So it's saying essentially he wants to do reverse breadth first search. Well, we just did breadth first search. So what I would do for that is I'd write breadth first search, right? Now, if I couldn't use a string and just append my stuff to a string, then all I would do is that rather than printing out this, I would add it to a stack. And then I'd print out each item in the stack, because the stacks are last in first out, it would come in reverse. So that is fairly straightforward. Let's see. End of a linked list. Linked list. So base Java expression head.next. Yes. Head.next. What's the value? Okay. Write a stack with the header that says append. Appends a node containing the character ch to the end of a singly linked list whose first node is parameter head. A head value of null represents an empty list. So this is essentially a recursive problem, or you could do it iteratively. But you would want to approach it with a recursive problem, where the base case is if the head is null, create a new head. Okay. And then otherwise, if head is not, otherwise what you're going to do is basically say if current, you basically say current is equal to head. I'll write it down so you can see it. So basically you'll say no. So after base case, essentially node current equal to head while current dot next is not equal to null, advance current, and that will make event m. So current is equal to current dot next. And what this is going to do is that this is going to basically keep moving current until it gets all the way to the end, right? So now current will be the tail. And now that once current is the tail, all we have to do is write, once current is the tail, what we say is basically, and I'll do it in one line so it'll fit, current dot next is equal to new node ch size plus plus. Right? After appending the new node, it should return a reference to the first node. So that's part of the reason why we don't want to mess with head. So we'll just simply return head at the end regardless. Right. It's a fairly straightforward kind of problem. Doesn't really take many lines at all. It's a good question though. If we wanted to improve the efficiency, additional information will we need to maintain about the linked list. We would want the tail, right? If we want, so this takes O of n time currently to do, right? Because I have to start at the head and add to the end. If we want to improve the efficiency, then we need more information. We can't do it. I wrote it as efficiently as possible with what we have. We want to improve that efficiency. We need a tail. Was the worst case time efficiency if we use that method now? It's constant time now, because we would just simply add a new node to the end. Okay, so we did this one. Search uses iteration instead of recursion, and we did mirror, and we did that. Okay, great. So we will look at this one, and now this is more stuff about algorithms. But this one I like. I like this question again. Insertion sort and merge sort. And then I think this will be the last problem we do for the day. And then on Monday, I'll go over some more questions as well as take some other questions that you might have. So consider insertion sort and merge sort. For each algorithm, what will the worst case asymptotic upper bound be? In other words, worst case big O time. If you know additionally about this, that the input is already sorted, it's reversely sorted, or it's n copies of the same number. For each case and each sorting algorithm, justify your answer and justify it in one sentence. Okay, so let's go through insertion sort, and then we'll talk about merge sort. Okay, so with insertion sort, that's typically an O of n squared worst case runtime. But insertion sort is like the king of O of n squared runtimes because it's actually very efficient under certain cases. It's adaptive, meaning if stuff is already sorted, it takes advantage of that. And if it's already sorted, basically it will look at the first item, say, oh, it's, first item, it's the beginning of the sorted area. The second item is going to be like, that's already sorted, don't have to push it down. Third item's already sorted, don't have to insert it. Fourth item's already is, and then it will keep going and basically looking at each item and saying, I don't have to push any of these down, just constant time check on each of them. So if it's already sorted, then you get the best case runtime for insertion sort, because the best case runtime for insertion sort is actually O of n. It's already sorted. If the input is reversely sorted, however, that is actually the worst case scenario for insertion sort whatsoever. It's always going to be O of n squared, no matter what, because the first item and the second item has to be inserted with 1 step, third item has to be inserted with 2, fourth item has to move down 3, fifth, and so on and so forth. Now, C is actually a trick question. An input containing n copies of the same number. That is a sorted list, right? Technically, it's also reversely sorted, but let's not think about that too much. Okay, so, but if it's n copies in the same number, I would argue, it really depends on how the insertion sort algorithm was written, but I would argue that that is all the same as sorted, and therefore it would take O of n. Now, merge sort in itself is just a big troll, because merge sort don't care. Merge sort is always n log n. Doesn't matter if it's already sorted, if it's reversely sorted, or n copies of the same number. Has no, it's going to handle that the same way. Always going to be n log n. Make sense? Okay. All right. So I think I'll leave it there for today. Because just a couple of before we dismiss, I'm not going to really have the moment to take demos, because I know I have to talk with some people.